Thank you, Ivan. Thank you, everyone, for joining in today. So I'm Shivam, and I'm also joined by Vishal, my colleague from H20.ai. And today we will be presenting and discussing best practices for NLP, AutoML, and some of the techniques that we have developed in-house that leverages AutoML along with NLP, and especially some ideas that work with multilingual data sets. Well, multilingual data is of prime interest for us because in APAC we deal with multiple languages, and for many NLP tasks, it is important to handle multilingual aspects in NLP. This session will be followed by a hands-on lab in the end, which where we can actually hands-on practice the NLP AutoML experiments with real data sets with real use cases, and all of you can also try it along with us as well. So as I discussed, there are two parts of this whole session. In the first part, I'll be discussing more about AutoML and NLP and multilingual data and some of the ways to work with multilingual data. It will be followed by the lab, hands-on lab on our platform, Driverless AI. So what I will suggest for those of you who wants to actually try the hands-on lab followed by this session, you can actually make an account on this URL called aquarium.h20.ai, which is highlighted here. So this is the link for our training platform where it allows users to train AutoML experiments in their dedicated labs, in their dedicated instances. So for those of us who will be trying hands-on lab, I will suggest to go to this link, create an account with your email ID, and you can browse the labs. And once you go through all the labs, you can click this Driverless AI 1.9.3, where we will be doing a real multilingual NLP use case. Okay, so let's continue with the first part of the session where we want to discuss AutoML and general idea of NLP as such. So if we talk about a general flow of a machine learning process, it can be categorized broadly into four major areas, and that's what H20.ai has also focused on, where the first idea is to collect data from multiple sources, which may come in a structured or unstructured form. Then it goes to the data preparation stage, where we need to focus on cleaning the data, making a lot of transformations, doing a lot of feature engineering, and doing a lot of blending and augmentation to enhance the data set that we have as such. Once the data is ready, we need to focus on the ML part, where the focus is on training the machine learning models, tuning the hyperparameters of every models. In some cases, we need to ensemble the models so that they work well and generalize well on different data sets. And in some cases, we also need to do a lot of post-processing to make sure the models are validated, the models are calibrated, and they align with the business need as such. And finally, we expect the models are transferable, the models are explainable, and they generate deployable artifacts which can give different outputs which can be deployed smoothly at various platforms or at various places as such. Well, this ML process is very straightforward, but one of the idea that goes into this process is that the middle piece is mostly very iterative in nature. It requires a lot of effort in terms of time, in terms of trying different ideas and coming up with the best possible solution. Well, that's where AutoML comes into picture, which really automates different tasks, different steps in a whole process that I just described. And basically, it gives a box which you can say that it's an AI in a box where a number of routine tasks, mundane tasks are automated. Well, there may be a lot of other tasks where data scientists can become more creative. For example, feature engineering. We really cannot automate, say, domain-specific feature engineering, but let's say the ideas of data-driven feature engineering, statistical feature engineering, or NLP feature engineering, those type of things can be automated. Then similarly, when we talk about model training part, sometimes we need to train hundreds of models. And that's where if we have AutoML in place, the focus can be on just plugging in the data. Hundreds of models can be trained within one single process, and they can really give a blend of models, and can give the outputs which are actually explainable, aligned with the business, and responsible AI is also part of it as such. And in the hands-on lab, we will actually try this whole AutoML process in the platform that is developed by H20.ai. When we discuss the domain of NLP, now in NLP we generally have to work with multiple tasks, multiple type of problem statements, especially like text classification, translation, entity extraction, summarization, question answering, and document similarity. So we have multiple types of NLP tasks, but one of the general idea when we want to apply AutoML with NLP or with text data is that we need to convert the unstructured data into some vector representations or some learned representation which can be used in a machine learning model, right? So when we talk about working with NLP in the context of AutoML, the idea is to automate these tasks of NLP, which involves the transformation of text data to vectors, train the models, evaluate them, and deploy them. When we talk about transformation of a text data, we are generally talking about representing all the words or say the characters or maybe n-grams in an n-dimensional vector space, which we also call as word embeddings. And word embeddings are the vector forms which really captures the context of the words, meanings of the words, so that they can be easily or smoothly used in say machine learning models, even deep learning models as such. When we talk about training in context of AutoML, we are talking about training very specific custom NLP model architectures for specific tasks. For example, if we talk about state-of-the-art model architectures like transformers, attention, autoencoders, BERT, so these are the architectures that are designed to work on these specific NLP tasks, and they are meant to give good results as compared to say normal machine learning algorithms. And the third idea that is also considered when we talk about NLP and AutoML context is fine-tuning of the pre-trained architectures. Well, one advantage in the NLP domain is that we do have a lot of corpus, a lot of data set which is available over the web in the form of say Wikipedia, Common Crawl, a lot of news data sets as such. So a lot of pre-trained architectures are available which can be used by the concepts of transfer learning. And once these data sets are used, they can be fine-tuned on the given data set of your domain as such. So AutoML in the context of NLP generally has these three ideas: convert word to vectors, apply NLP specific model, or use transfer learning to derive meaningful outputs from the pre-trained architectures. Now, when we talk about multilingual NLP, when we are talking about different aspects of NLP in different languages, we are basically talking about same type of tasks that we discussed, like maybe translation, classification, tagging, in different domains, say healthcare, finance, social media, legal. But the special piece is that now the text can be in different languages. It can be say German, Polish, Hindi, Malay, Bhasha, and many form of languages available. Now, when we are talking about these multilingual languages, we need to make sure that either the models that we have trained, they can really understand the multilingual text, mainly the non-English text, or let's say the embeddings or the features that we probably used, they also capture the context of different languages. So I would like to share three use cases that we recently delivered, which involved multilingual data. So one was multilingual complaints classifier. So this was done for a bank which was operating in whole Southeast Asian region, and they wanted to analyze different customer issues that were coming from their reviews, their complaints that they post on their forums and so on. So we used our approach, H20.ai platform approach, where we analyzed all that data in almost 7 languages, and we were able to derive different issues, and we were able to categorize them into the particular category that they belong to. The second use case that we worked with, which had multilingual NLP aspect, was anti-money laundering, where the idea was to develop a model which can detect the likelihood of fraud by analyzing different news data from different countries. So here we were working with different languages of news, and we used our same multilingual recipe, multilingual approach to identify key topics mentioned in those news in different languages, and those topics were then used to map whether there is a likelihood of fraud or not. And the third use case that we did was a cross-selling recommendation model for an e-commerce company, who started their operations in one country, but they wanted to expand to multiple countries. And one of the challenges they had to deal with was the multilingual aspect, where they really wanted to take care the product descriptions, the product details, and so on in different languages and so on. And that's where again we used our approach that we will be walking through shortly to build this cross-selling recommendation model. Now, what are some of the best practices, some of the ways that we have incorporated in our platform to work with multilingual NLP? Well, the first one is pretty standard, pretty straightforward, and traditional approach, I would say, is the translation. Now, machine translation generally means that any data that we feed into the system, we first detect the language. So it becomes kind of a classification problem, and we detect what type of language it is. And then there is a dedicated model to convert that language to, say, English language. And there are many good state-of-the-art approaches or techniques available on internet, as well as in many research papers, like statistical machine translation, rule-based machine translation, neural machine translation, or recently the transformer model with attention weights, where let's say the text from every language can be tokenized into different words, and it can really find what are the most important areas within that whole sentence, and which needs, let's say, the translation to be done at that particular area. This is one standard approach, but it has some cons, as in, like, once we do this translation of one text to the other, there is a loss of context. There is a loss of information, because there are multiple layers or multiple stacks of models that are being placed at every layer, either, say, for detection or for, say, translation. The time taken for this whole pipeline is much larger, and the complexity is also very high as such. And some of the low accuracy is also achieved in some of the languages where we don't have enough data, enough corpus to train with as such. So this is one of the general idea. We don't directly use translation in the approach that we have developed, but rather we use it as a separate recipe in the case where we want to, let's say, work on a non-English text, and we want to really translate to understand the meaning and so on. The second approach that we have generally used, and we have seen it works well, is the character level embeddings. Now, this character level embeddings we developed for some of the classification problems when we were working with especially Japanese language and Mandarin language, where characters play a lot of role, major role, and also there are no spaces between different words and so on. That's where we cannot really focus on, say, n-grams or words. We really need to focus on individual characters, individual spatial symbols, to understand, let's say, what spatial character means and so on. And the general idea that we developed is that we can represent every character into a vector notation, into an embedding form, and either we can use that vector or embedding directly in one of the model, or what we did is that we passed those to some of the standard CNN or LSTM models and derived the class probabilities with the help of the target column or the label column, and then use that probability as one of the feature in, say, normal machine learning model, say XGBoost or, say, LightGBM as such. So in this approach, our idea was mainly to capture the context which is associated with different characters, and either use them along with, say, other features that are available in the data, or use them directly in the model that we want to use as such. And as I shared, this works best for, say, classification type of tasks. This approach does not really works for extraction type of task, where, let's say, we want to extract the topics or entities and so on. Well, this is obvious, because we are converting the characters, we are converting one form of the data to the other form, and we are using that form to learn some patterns from the data with the help of machine learning algorithms as such. The third approach or third technique that we have bundled in our entire suite of multilingual pipeline is the multilingual embeddings. The idea of multilingual embeddings is, let's say, if we have text in a different language, non-English language, we generate a pre-trained embeddings only for that language, and Now, one thing which we can do is we can just use that language specific embedding for our task. Now, this language specific embedding idea work mainly for those cases when we have, let's say, a text column and that is purely in one language, maybe say Mandarin, maybe in Japanese, and so on. But we have also incorporated language agnostic embeddings, which works well for, say, text columns, which may have mixed languages within a single column. Well, one example of this can be the reviews, because sometimes, let's say, there is a mobile app for, say, a bank, and they are operating in, say, multiple countries, and the reviews can come in from those countries, and then what we collect is basically one text column. It may have mixed languages, text, and so on. Now, for those cases, language agnostic embeddings really work well. And one of the embeddings that we use is the laser embeddings from Facebook, which basically maps all the text into a 1024 dimensional space. And in this space, basically, if there are text that have similar context, even though they have different meanings, they are represented at almost similar location. And we don't really need to take care of, say, what language it was when the data was passed into. We can just reuse or take these embeddings and pass them to our models for, say, standard classification or extraction type of tasks as such. So multilingual embeddings is very, very popular, and with the example of laser embeddings and some other popular ones like multilingual BERT embeddings, multilingual data can be really converted into, say, one normalized form, which can be used for NLP related tasks as such. Well, an advancement or improvement over multilingual embeddings is multilingual models. This is another approach that we have used in our multilingual approach of driverless AI H2O platform, where we basically have dedicated models. We have trained dedicated models where we combined the data, input data from multiple languages. One major problem that we faced in combining these data was a lot of imbalance, because it is obvious that English text language is much larger as compared to, say, some low resource languages. So we did a lot of undersampling of English, and we did a lot of augmentation, text based augmentation for lower resource languages to make it balanced. We trained state of the art model architectures like BERT, and then the output of these models can be used directly as, say, our probability of the class, or maybe they can be used as a feature in some other machine learning model as such. So idea of multilingual models is the same that we use, is like we train a single model that can handle multiple languages simultaneously, and in the end, basically, we are talking about a unified model for different sentences in these languages. And two of the standard models that we use are BERT-based multilingual cased, which was trained on 104 languages, and it has about 110 million parameters. And the other one is XLM Roberta, which is also trained on about 100 languages, and it was trained on much larger data, about 2 terabyte plus on Common Crawl. So these two models are external models that we use along with the models that we have trained within H20.ai platform. The last idea I would like to describe is the idea of transfer learning, where we can do cross-lingual transfer. In cross-lingual transfer, the main idea is that we train one model on a high-resource language, let's say English or maybe, say, Russian, and then we reuse the weights. We transfer the weights or, say, embeddings or annotations, and fine-tune that on a different language, maybe, say, Russian, or maybe, say, other type of language as such. So this idea of transfer learning we have used in some of the local-ish APAC languages as well, and we have achieved some of the state-of-the-art results. And in fact, in today's hands-on session, we will also see how to use some of these transfer learning ideas within our platform as such. There is another idea of zero-shot learning or zero-shot transfer, where we can focus on models that really works well for, say, a language where we don't have enough annotated data, we don't have much of the annotated data, and still it works well for examples which were not part of, say, training data, or they did not have any similarity within training data. Now what we can do is we can fine tune or train these models for monolingual data, where we can again combine different languages, and then those monolingual models can be used for, say, other languages where we have, let's say, annotated data, or maybe we don't have, say, enough annotated data. The idea is that transfer learning in the context of zero shot can be used to work for, say, multiple languages as such. So right now, so far I have discussed all these 5 techniques to work with multilingual NLP, and these are the general techniques that we as a company have also incorporated in our platform, in our AutoML, where we have blended all of these techniques. Inside our AutoML, what we have done is we need to pass in the text data, and we have different recipes. We have pipeline building recipes. One of them is NLP Transformer Pipeline, which can consume this data and convert it into different features, different embeddings, different vectors based on the character level embedding idea, or say monolingual embedding idea that I discussed just now. We have also an auto model pipeline where we can avoid generating the embeddings from the data, but we can straightforwardly use the monolingual model that I discussed, or we can use, say, monolingual BERT or XLM Roberta, and it can give the model which can be used for, say, our main task, the global task. And we also have custom embeddings, just in case, let's say, there is a domain specific embedding that we want to use, or domain specific model that we want to use, maybe, say, for finance finbert, or maybe contract BERT, or maybe healthcare BERT. We want to use those embeddings and we want to fine tune that. We can also bring in within the platform, and they can generate the domain specific embeddings. And when we combine all of these techniques together, and they can be used to give state of the art result. And in today's hands-on session later in this webinar, we can also discuss, we can also go through all these pipeline as such. Now, if I talk about a little bit more with the first approach that we have in the transformer pipeline, different type of embeddings that we use include the standard ones, means TF-IDF or count vectorizer. We use some of the pre-trained word embeddings. We use the character embeddings that I discussed. And we also use word embeddings to generate, let's say, domain-specific features or domain-specific vectors. And I also described that sometimes we don't use these embeddings or these counts straightforwardly, but we pass them to different models for some smoothing effect, or maybe for some to compress those embeddings into lower dimensions so that they can be used. And for that second layer approach, we can use truncated SVD or linear models. We can use CNN models over word embeddings to give class probabilities. On character embeddings, which I described earlier, we can also use CNN, LSTM, or, say, BERT embeddings. We can use linear logistic models to give class probabilities, which can become feature to our main machine learning model as such. So we have mostly developed this using PyTorch, and all of this support PyTorch backend. So if required, if there is any new embedding to be added, that can be easily added on top of what is available. The second part of our approach includes the AutoModel pipeline, where we already have a number of pre-trained state-of-the-art BERT-based, XLM-based architectures, which are used to convert a text column into, say, meaningful outputs, maybe the class probabilities. And within these state-of-the-art models, we also have incorporated the multilingual models, as I described, the XLM Roberta, or BERT-based multilingual, which can really work on, say, a text column where we have data from multiple languages. And the third idea that I was discussing was the use of custom recipes, or transfer learning, where we can bring in, say, domain-specific models, domain-specific architectures, say medical BERT or finance BERT or bio BERT. And what we can do is either we can use the outputs of these embeddings directly, or if we want to fine tune them on our data that we have provided, we can freeze the last layer and fine tune them based on the data that we have provided within this platform as such. Right. So with all these techniques, with all these ideas that I discussed, we have incorporated them, bundled them into one package AI in a box AutoML platform called driverless AI, which works well for any text data and can really solve all these problems.